All right, welcome to our first trig video. I'm going to go through what we're looking at in the video first. So I'll typically start off these little lectures by just kind of highlighting a couple of areas that we're going to focus on. So first, we're going to talk about just some general vocabulary. We're going to talk about radian measurements. My guess is that if you've done some trig before, you've mostly worked in degree measurements. So we're going to talk a little bit about radians. I expect that you've heard of them, seen them a little bit. We'll just kind of dig into that. We're going to do a bit of unit conversions back and forth between degrees and radians. And then our last things that we'll focus on are arc length, or the measure of a arc of a circle, or a section of a circle, and then area of sectors of circles. So this is just our first bit. We're focusing on angles and radian measurements. So mostly it's just going to be some vocabulary stuff. We'll build up from there. We won't really get too heavy yet. So here's some vocabulary stuff. We're going to be plotting all of our angles on the regular Cartesian coordinate system. So when we draw our angles, we'll be drawing them here. We'll talk more about what standard position is in a second, but I'm going to draw some stuff and kind of explain what's going on. Hopefully you've seen this from geometry classes. A ray is just a portion of a line that starts at a single point. Maybe we'll draw our single point. We'll call that the vertex right here. It's not a very good point. There we go. And then a ray might look something like this, extending out in one direction, and it extends infinitely far. So that's why we've got a little arrow on the end. So this is our ray. An angle is just two rays drawn together. So maybe we could look at that ray, and then I'll draw another one right here. And so our angle is formed right in the middle. In this case, maybe we'll call this one here the initial side. And this one here we can call, the terminal side. I apologize, my handwriting is pretty bad normally, but it always takes me a little bit to get used to writing on this little tablet thing again, so hang with me. Normally we won't draw them like this. Normally we'll draw our initial side right here on our standard x-axis, and our terminal side might go something like that. And so our vertex could be right here at the origin, and then we've got our little arrowheads. Let's say, hey, this thing is going off in infinite direction, in those infinitely far in those directions, and then our angle is just this kind of distance in between. Not really a distance, but kind of the measurement of how far apart those are extending away from each other. Again, I said we're going to draw these things in standard position for the most part. Standard position is putting the vertex at the origin here and having the initial side be the positive side of the x-axis. So that's what we mean when we say standard position. We're always starting like this. When we talk about the rotation direction, then, we have a couple of different things here. This type of angle that I'm drawing right here, where I go this way, we're going to say this is a positive angle. We're rotating counterclockwise. That's going to be our normal direction of rotation. If I draw an angle in initial position, and let me switch back to green here, and I draw my initial side here on the x-axis, and I draw my terminal side at the same spot, this looks like the same angle, but what I could do is I could go backwards around here. I could go in that direction. And if we do that, we'll end up having some sort of a negative angle. So the rotation direction is going to be really important when we talk about the actual measurement. That's going to tell us whether we've got a positive or a negative angle. I'm going to denote these angles with theta. That's our Greek letter. Ooh, let me draw a better one. Let me do that over here. There we go. That's better. So this is our Greek letter theta. That's going to be like our standard variable for an angle, just like x and y are standard variables that we use with functions. So a right angle, we're going to say that's when theta is equal to 90 degrees. You don't really need to know what the measurement of that is. I mean, you probably do already, but that would be if we have this thing completely perpendicular. So let me draw the terminal side on the y-axis. And normally we denote that it's a right angle with like a little square box. I suspect that you've seen that before. So this is our nice right angle. An acute angle that's when theta is less than 90 degrees. So that's like that first picture that we had. And an obtuse angle is when theta is going to be bigger than 90 degrees. So let me get rid of this stuff and let me draw something that's a little bit bigger than 90 degrees. Maybe, oops, let me make that a straight line. Maybe it looks something like this. And so you can see we've rotated past that perpendicular spot. And so that's when theta is greater than 90 degrees. Again, I suspect that you've seen this terminology before, what a right angle is, what an acute angle is, what an obtuse angle is. But if not, that's what we've got. The main thing that we want to push towards, though, right off the bat, is to talk about radians. I suspect, again, that you've seen some of this stuff, but my guess is that you do not remember the definition of a radian. Here's what it is. I'm going to just read through this, and then I'll kind of talk about it and draw it, and hopefully we can get this good idea. A single radian is the measure of the central angle of a circle. That's just what we've drawn there. That creates an arc equal to the length of the radius of the circle. Now, I should note that here we have a circle going on. And in our other pictures, there's no circles here. We just have the regular old rays going off from the origin. So what I'm going to do is I'm going to draw that same kind of angle here, but I'm also going to draw a circle around the origin. Now, I can't draw shapes on this very easily, like nice standard ones, so my circle's probably going to suck, but that's all right. Bear with me. All right, that could be a lot worse. Let's pretend that that's a decent circle. I'm going to draw my angle in standard position again, extending out this way. Maybe I'll make it clear that my vertex is at the origin. I'll put that little dot there, and then I'll have it going. Let's do that way. So there's my angle here. Now, a single radian is when this angle measures where the length that I'm going to highlight here, this arc length, is the exact same thing as the radius here. So this is almost like, kind of like an isosceles triangle where all these lengths are the same, except this is clearly not a triangle. It's just a portion of a circle. So let me kind of draw that here off to the side. And so when we have something that looks like this, where these three lengths are the same. Oops, I cut a little bit off there. So all three of these lengths are the same. Maybe you've done this in classes before where you mark the lengths that are the same with these little tick marks. That angle right here is 1 radian. That's a weird thing to visualize. It's a weird thing to think about. This note is the really important part, though. What this means is that, there's our nice theta. Theta as an angle is just a ratio of the arc length, that's this red bit here, S, and the radius, that's this blue bit here, R. You can get that right from the definition. If we have 1 radian, that means that the arc length, our red arc length, and our radius, this blue length that we had, are the same. And so if they are the same, that's equal to 1. So really, when we're measuring an angle here, we're really just looking at a kind of ratio of this length here compared to the radius. So a single radian is when they're all the same thing. The radius and the arc length are the same, that curved length there. But if we had maybe this red arc length double the size of the radius, maybe if we had something like this, let me try and get a decent picture of what that might be. That'll probably be right around there. I don't know. It's hard to just guess. And if I draw a nice curved arc length, hey, that's pretty good. This like could be 1 here, and this would be 2. So now our arc length S is twice the size of our radius. Or maybe these are both 2 and this arc length then is 4. Either way, same angle. Theta is 2. Cool. So if we want to think about right angles, acute angles, and obtuse angles, we're really going to be focusing on the exact same picture that we had before of these perpendicular rays. So let me draw our nice right angle. There's our 90-degree angle that we're used to. But in radians, we have to figure out what this is. So this is kind of a little bit tricky here. We can think about the actual circle. So let me go back to this picture here. And let me go ahead and... Actually, you know what? I'm going to draw it over here. So let me draw a nice circle here. And what we want to do is first think about what the angle would be that goes all the way around our circle. So let's say there's our initial side. Let me draw our little vertex in the middle. I should put my vertex on this one too. And my arrow. And I'm going to go all the way around 360 degrees. And there's my terminal side. Let's pretend that this is a radius of 1. So we have to figure out what's the arc length here. Because then we can say theta is going to be s over r, arc length over the radius. So if we go all the way around this thing, what is the arc length of this full circle? Well, really what we're talking about is just circumference. And circumference is really easy. It's just pi times the diameter. Well, the diameter is twice the radius. So this is, there we go, 2 pi r, which if the radius is 1, then we'll just say this is 2 pi. Cool? Cool. So this angle here, this arc length is just 2 pi. Now what you'll notice is that if we want to find theta in this case, theta is really 2 pi r over r. So it doesn't matter what the radius is. It's always 2 pi. So that's our whole circle. If we want to just find this angle here, we can notice that that's really just a quarter of that. So this is when we have theta is 2 pi divided by 4, or really pi over 2. So that's what this right angle is. And then we can use the same idea. We can say an acute angle is just something that's smaller than that 90-degree measurement, or when we're thinking about radians. Let me draw that again. That looked like a 2-year-old drew it. There we go. We'll say theta is less than pi over 2. And for an obtuse angle, we'll say theta is greater than pi over 2. So pi over 2 is our nice right angle that we'll use this terminology to compare to. If something is bigger than pi over 2, we'll call it an obtuse angle. If something is less than pi over 2, we'll call it an acute angle, because pi over 2 matches up with 90 degrees. So that's what we've got for radians. And this is basically what we've got going on here. If we know a couple of angle measurements in both radians and degrees, then we can convert really easily, just like we did with this. We said, okay, the whole distance around this is 2 pi. That's really the same thing as 360. So then you can just go ahead and figure things out from there. 90 is a quarter of 360, so in radians, it's a quarter of 2 pi. That's what we did to figure out that this right angle is pi over 2. There's some formulas and all this kind of stuff here. Honestly, I don't think it's that important. As long as you can convert back and forth between these things in whatever way that you'd like, that's fine. So I forget if this is exactly what our textbook does or if it's something a little bit different. But let me just kind of read through this. You can do this by scaling an angle appropriately as long as you know one. So we can use a scaling factor A to apply it on both sides of an equation. So for instance, we know that 180 degrees is pi radians. If we go back, pi over 2 is 90 degrees, so all the way out to 180 degrees is going to be 2 pi over 2s. Or you could say it's half of 2 pi, half of 360. So we know that 180 degrees and pi radians are the same thing. So if you just multiply both of those things by some scaling factor, then we're good. If you want to find, 30 degrees, that's a sixth of 180 degrees. So that should be a sixth of pi radians, or pi over 6. So you can do something like that. If you have an angle in degrees, then we'll just look at the ratio, meaning we can go ahead and just do this. To find your angle in radians, look at that ratio, multiply it by pi. If you have an angle in radians, then you'll take your angle in radians divided by pi and then multiply that by 180, and that'll work things out pretty easily. Let me show you what I mean, though. 45 degrees. What I always would think is that 45 degrees, this is a quarter of 180 degrees. Let me put my little degree symbol there. And so that means that this is, in radians, a quarter of pi. Similarly, I'll go over to this one. 2 pi over 5 is really 2/5 times pi. So in degrees, that's going to be 2/5 times 180 degrees, which is 360 degrees over 5. I don't have a calculator, so I have to do this in my head. 360 degrees divided by 10 would be 36 degrees, but we don't want to divide it by that much, so this is actually going to be 72 degrees because we only want to divide it by 5. You can just do it with a calculator. I just don't have one in front of me. So go ahead and see if you can use that to figure all of these things out. If you have a hard time figuring out this ratio here, noticing that 45 is really a quarter of 180, what you could do is just say this is really 45 degrees over 180 degrees. And there's your ratio that we've got here. So go ahead and do that with all of these things. You can mess around with the radian ones to degrees, mess around with the degree ones to radians. Pause the video and try these, and when you come back, I'll fill all these out just so you can at least check your answers. I might show like a couple of them with some work and a couple of them without, but that's what we're looking at. Cool. All right, so I've just gone ahead and filled these out. I'll show off these first two that we have, the 60 degrees and the 1.1 pi, but the rest of them you should be able to just check. So if we want to figure out this ratio, we could say, all right, what is 60 over 180? But it's pretty easy to see that that's just 1/3 of 180 degrees. So in radians, this is just going to be 1/3 of pi. And so we'll say pi over 3. You'll notice I rewrote this as pi over 4 just to save some space. Similarly, over here, we'll say this is really 1.1 times 180 degrees. And so that's 180 plus 18, so 198 degrees in degrees. 36 degrees, you can say 36 is really a fifth of 180. 36 over 180 is 1/5, so pi over 5. 130 over 180 is really 13 over 18, so 13 pi over 18. And similarly, 4 over 180 is, oh, I didn't reduce this actually, sorry. This is actually pi over 45. Whoops. You can reduce that fraction a little bit more. I don't know why I left it like that. And then 4/3 times pi, that's really 4/3 times 180. 3/4 times 180 here, and then negative 1/6 times 180. Go through those, double check that, make sure that you can convert back and forth, and that should work out pretty nicely. There are other methods of doing this where you set up proportions and all that kind of stuff. All I really care about, honestly, is that you can actually convert these things. So make sure that you can get through it and that you can get through it easily, and then you should be good. Coterminal angles. We've already drawn a picture of coterminal angles, but let me just kind of go through it formally. Coterminal angles are two different measurements that have the same initial and terminal sides. So let me show you what I mean here. Let me draw a picture that I kind of drew already. Whoops, that's not the button I wanted. Here we go. So here's my regular old initial side, and maybe I'll do like, this is going to be approximately 60 degrees. Oops. So in radians, maybe I'll write this as pi over 3. Whoops. There we go. Or 60 degrees. I'm going to draw the exact same picture, but I'm going to draw it a little bit differently in how I label things. So maybe I have a negative angle instead. I go backwards around here. So then what we really have is negative 300 degrees, if we did that. Or what we could say, maybe I should write that actually over here, negative 300 degrees. Or if we wanted it in radians, we could say this is really negative 5 pi over 3. Oops, let me clear that up. You'll notice that these are really just 360 degrees away from each other, or they're 2 pi away from each other, or if you want to think of it, that's 6 pi over 3. So the difference between these angles is really just one whole revolution, which maybe makes sense if we take this little terminal side and we rotate all the way around we get back to the same thing. Now, that leads on to a whole bunch of different ways that you can get coterminal angles, because if you wanted, you could also, maybe I'll do this one in blue, you could go all the way around and back again. So it's a positive angle, but now it's 360 degrees for your full revolution, plus another 60. So what are we looking at there? 420 degrees. In radians, that's 2 pi, a whole revolution, plus pi over 3. So that's 6 pi over 3 plus pi over 3. We're looking at 7 pi over 3. So these angles are all coterminal because the terminal sides are the exact same thing, even though they have different measurements. So just a simple picture of an initial side and a terminal side is not enough for us to really tell what the angle is. Although they all look the same, they might have some backwards revolutions. They might have multiple revolutions on here. You could go around as much as you'd like. Maybe we revolve around this thing like 6 different times before we end up at this terminal side. So all of those angles look the same, even though they act a little bit differently in their measurements. And now we get into the main things here. We want to talk about arc length. We want to talk about area of a sector. Arc length we've kind of already covered, because if you remember, I'm going to scoot back really quickly here. If you remember, where is it? Here, when we talked about what a radian is, it's the length of the radius, and it's the, there we go, a length of an arc here. So a single radian was when the arc length was the exact same thing as the radius. So if we go back down to this thing and we look at some sort of an angle here, it should be pretty easy to tell what's going on. Let me get rid of that. Okay, so here's my vertex like normal, there, and let's say my radius is r. This arc length, maybe I'll do that nice little highlighter thing again, and I'll do it in red. If we want to find this distance, and we know what the angle is, we happen to know that this angle right here is theta, then we can say, well, theta was supposed to be s over r. So if you just multiply r on both sides, it's pretty easy to see that s is equal to r theta. Not surprisingly, if we make the radius 1, then s and theta are the same thing. The arc length is the same thing as the angle, which, if you go back to the definition of a radian, should make a decent amount of sense. So hopefully this arc length formula is not too hard to figure out. We'll just multiply the radius by the angle. Essentially, we're just scaling this angle by this distance, because this arc length is smaller than, say, we had a circle that had a bigger radius out here, same angle, but it's pretty easy to see. 1 second. It's pretty easy to see that this arc length that I've drawn with the bigger radius is bigger than this one. And the way that they're sized, or the way that they're scaled, is just by the radius. This is kind of similar to some geometry stuff where you talked about similar triangles where lengths are just scaled and blah, blah, blah. It's the same kind of behavior happening here. So that's kind of neat. And then the last one is area of a sector. We know that in general, the area of a full circle is pi r squared. That's for the whole thing. So if we want just a sector, I forgot to make straight lines on here. Let me do that. There we go. So if we want just this area, we're really just trying to figure out what kind of proportion do we have here. If this is the full one, where our angle is 2 pi, then you'll notice that if we put in 2 pi, we need the 2 to cancel out. Oh, I've got something wrong here, I think. Yeah, that's supposed to be gone. Let me rewrite this. So this is actually supposed to be, our area is going to be half of theta r squared. There we go. So if we put in 2 pi in for theta, we're going to get half of 2 pi r squared. The half and the 2 will cancel out. We just end up with 2 or pi r squared the way that we normally would. If we're looking for just some sort of a sector, and we know what this angle is here, that's our theta, then we can just use this formula right here, and that'll give it to us. The half is, again, just coming from the fact that for our full circle, the measurement is 2 pi, and we only need pi r squared. So we have to use this half to cancel out that coefficient on the angle 2 pi, so that we get our regular area formula. So here, we can think about similar triangles if you want, or you can just think about the definition of what a radian is, and that'll pretty much give you the formula for arc length. And here, you can just remember your area of the full circle, and that'll pretty much just give you the area of a sector. Give a shot to some homework problems. Try some of this. Get some examples going. I know I didn't really do any examples of arc length and area of a sector. I think it's mostly computation stuff where once you have the formulas, you can just dig into them. But hopefully, as you do them, you start seeing why those formulas are holding. If you got any questions on anything from this video, put them up in the discussion board on Canvas. I'll be able to answer your questions there. You can answer each other's questions there. And hopefully we're already off to a pretty good start in this class. We'll see how things go from here.